It's a pleasure to be here this afternoon talking to you about a topic that I really enjoy, lasers. So as David said, a lot of my research in my career to this point has involved using laser technology. And when I took my kids, I have an 11-year-old son and an 8-year-old son. A couple of years ago, we went to see Star Wars: The Force Awakens, and my younger son came up to me after the film and said, "Dad, those things in the movie, are the lasers in your lab like that?" And you know, at the time, I had to break it to him that those things you see in the movies, right? They're not lasers. They were predictably kind of surprised. And I guess thinking back on it, I didn't really learn anything about lasers until I started my PhD studies. So although I don't clearly remember what I thought about Star Wars at the time, I probably also thought that the technology that we see in this science fiction universe were lasers. So what are we talking about here? We've got a few different types of technology that we see in Star Wars that might be lasers. We've got blasters, featured here by a stormtrooper, this ship down at the bottom with plenty of blasters, and even this laser pistol device that was marketed to kids in the 1970s. We've got the lightsabers modeled here by a few different generations of filmmakers. And we've got the iconic Death Star with its main cannon, and in the newer iteration of the Star Wars movies, the Starkiller Base. So all of these devices look kind of like they could be lasers. They're all light, shiny things that are going in straight lines, and we know that laser pointers basically do that. So what makes these things different from lasers? Well, I'd like to present you with a few pieces of evidence that I think strongly suggest that these devices don't obey the same laws of physics that our lasers here on Earth do. So the first thing is lasers, as you may know, travel at the speed of light. And the speed of light is really fast, something like 186,000 miles per second. And these blaster bolts that Miss Daisy Ridley is so casually deflecting in the bottom are not moving anywhere near that fast. In fact, even a bullet fired out of a gun is traveling at a much higher speed than those blaster bolts. And also, even if we could see these bolts, the response time of the human eye is some tens of milliseconds. And if we just say 20 milliseconds is the fastest our eye can respond to something, if we have a little pulse of light that's traveling along at 186,200 miles per second, kind of the shortest distance we could ever see that taking is about 40,000 miles. That's how long the streak would be if we could actually see one little pulse of laser light. And these blasters in the hallway that the Rebel Alliance are firing are nowhere near 40,000 miles long. So I don't think that these are blasters. Likewise, the Death Star main cannon, not quite a laser. This is going way too slow. You can see all the light coming together, a beam traveling. That's just too slow. The other thing that's a little more subtle is lasers aren't visible from the side in space. On Earth, here you can see a light show down at the bottom. We can see the beam traveling through the air because light can scatter off of air and dust particles. It takes a really bright laser for us to see it traveling through air. In space, on the other hand, there's not really air around, and there's almost no dust. I mean, space is largely a vacuum. So these blaster bolts that are whizzing by this fighter pilot, if we could actually see those in space, we would only see them if they're hitting us in the eye, and then we'd have some other problems. Lasers also tend not to just stop in midair for no reason. So Mr. Kylo Ren's lightsaber here, that nice crossguard addition, if this were a laser, it would be extending into his leg. He would be in a little bit of pain. And finally, laser beams kind of pass right through one another. So when we have our epic cat lightsaber fights, the lightsabers, if they were actually made of light, would not bounce off of each other. So I think I've belabored the point enough here that the devices we have in Star Wars don't seem to act like real lasers that we have here on Earth. So if I'm telling you so much about what lasers are not, let me tell you a little about what they are. So what is a laser? Many of you have probably heard that laser is an acronym. It stands for light amplification by stimulated emission of radiation. And I'm going to break this down a little bit, but at the simplest level, we can understand what a laser is by thinking about this microphone and speaker system. A microphone and speaker is a device that converts sound, takes it, and amplifies it to high power using the energy of electricity. A laser is kind of a similar device, but it works with light. It takes a little bit of light and amplifies it to make it brighter. So you can think of a laser kind of like a speaker, but for light. And if we want to look inside a laser and how it works, we have to think a little bit about atoms and molecules. So I'm going to represent an atom with Mr. Goku. All right? There's a well-known process called absorption by which our atom, Mr. Goku, can absorb energy from light. It can absorb a photon of light and reach a higher energy state. So the atom can store a lot of energy that it can extract from a light field. So this is a simple process to understand. But Mr. Albert Einstein, you might have heard of him, he came up with this idea that if an atom can absorb light, there also has to be this process where an atom that's already in an excited state can be hit by a particle of light, a photon, and that photon will cause the atom to give up that energy that it has in the form of a second photon. So in this process, we take a photon, shine it on an atom in an excited state, and we get out two photons. And this concept is what allows a laser to work, because we can put one photon into a system and get more than one photon out. That is amplification. Now, although Einstein proposed this stimulated emission way back in the early 1900s, it wasn't until about 1960 when the first laser was actually made. And it was made with three main ingredients. Okay? We have three parts here. We've got an optical cavity, a pair of mirrors. One of them is, say, 100% reflective. The other one reflects 99.9% of the light that hits it. We have a gain medium, which contains the atoms that are going to do the stimulated emission process. And then we have an energy source. And so the way the laser works is we turn on the energy source. We apply energy to the gain medium. That energy puts these atoms into their excited state, and it causes the gain medium to glow. They start, the atoms in the gain medium start giving off energy. So when one of them gives off its energy in the form of light, if that light goes in the direction of one of the mirrors, it can be reflected back into the gain medium, where it can cause this stimulated emission process to happen. It takes energy from one of the other atoms, so now we've got two photons, where we started with one. Those two photons can hit the mirror, be reflected back, and be amplified again. Meanwhile, our energy source is regenerating these atoms back into the excited state. So we can carry on this process more and more, reflect the light back, go through, get even more photons. Now we started with one, we're up to 8. And as you can imagine, doing this over and over and over, we keep amplifying the light, making it brighter and brighter and brighter, until eventually we get a laser beam. And a little bit of that laser beam radiation leaks out one of the mirrors, and that's the beam that we see traveling across the room. And so lasers are basically amplifiers for light. And they have a few special properties which makes them really useful for science and technology applications. And I want to just highlight a couple of them. One, lasers are monochromatic. So unlike a light bulb, the light bulbs in this room, which give off light kind of all across the rainbow, a laser has one color. And that's it's a very advantageous property for science. Also, the laser beam, as we know, doesn't really spread out as it travels. If you take a light bulb and you move it far away, it gets fainter and fainter. But a laser keeps all of that concentrated light energy in kind of a little tube that travels, so that the energy remains concentrated even over long distances. And finally, we can make lasers all across the electromagnetic spectrum. We can make lasers all the way from the X-ray part of the spectrum through the ultraviolet part of the spectrum we can't see, through the visible into the infrared, where it once again becomes invisible to us, even out into the microwave and radio bands, where they're called masers instead of lasers. And to illustrate kind of a little bit why these properties are important, let's consider the comparison to a typical light bulb, like these floodlights that you see at stadiums. A 300 to 500 watt floodlight is used in a bank to illuminate a football stadium, while a 250-watt CO2 laser moving at 1 inch per second will slice up a hot dog. So it's kind of a good thing for us that conventional light sources that we like to use for illumination aren't concentrated like a laser light. But these lasers allow us to do neat things. I've built a few different kinds of laser systems in my career. Here's one that I built at the University of Illinois as a graduate student. So we have a red and a green laser that you can see in the image on the right. We got a little carried away with the liquid nitrogen that we use to make these things visible. So it kind of looks like there's a lot of action going on. But we combine those two laser beams in a crystal that you can see in the upper left image. And when the beams come out, looking at the lower left, you can see both the green and red beams, but there's also a third laser that you can't see that's in the infrared. So we used 2 visible lasers to create an infrared laser. We took that laser and sent it over to a plasma tube. So this tube contains hydrogen gas that we lit up at about 1,000 volts to make kind of a tube of plasma that, to me at least, it looks a little bit like a lightsaber. But inside this hydrogen-containing plasma, we make a variety of exotic molecules, some of which we've actually observed in space. And by taking our infrared laser and passing it through the middle of that plasma, we can study the molecules that are present in space in our laboratory. So that's one application I've used lasers for in my career, but I'd like to highlight a few other areas where lasers are used. And I'd like to kind of compare them to some of the devices in Star Wars, because even though the devices in Star Wars aren't lasers, some of the things that we use lasers for are pretty similar in some ways. So one, blasters, right? So a blaster takes this energy and shoots it across the room and it burns a hole in something. Well, we use lasers that way. In fact, there's this technique, a spectroscopic technique called laser-induced breakdown spectroscopy, where we take a laser, shine it on a sample that we want to analyze, and we do this in a way that creates a plasma. So on the right here, you can see a photo and then a little computer simulation of a plasma that's emitted off of the surface when it gets blasted by a laser. And by looking at the colors of light that are given off by this plasma, we can learn about the elemental composition of the sample that we shot. So we can tell these different elements on the periodic table, we can tell what's inside by looking at the color. We've taken this technology and we've put it on the Curiosity Mars rover, an instrument that has strong connections here to UC Davis. And there's an instrument on board called the ChemCam, which has one of these laser-induced breakdown spectrometers that is, as we speak, blasting rocks on Mars and measuring their composition. So in the spectrum that you see on top, there are lots of different peaks that show up at different colors that correspond to all of these different elements on the periodic table. And so we're using lasers on a robot on Mars to measure the composition of Martian rocks and soil. So kind of like a Star Wars blaster, right? So another thing, so we got the lightsabers, right? Lightsabers are useful for cutting things, like in this home video footage of a young Jedi in training. Useful for cutting the Thanksgiving turkey. And as we'll see in Star Wars: The Force Awakens here, that Kylo Ren shows us we can use lightsabers for interior design applications. But lightsabers are used for cutting things, essentially, and we can use lasers for the same applications. Lasers are used in the medical field as a kind of light scalpel. So instead of using a knife to make incisions, we can use lasers instead, which is a really good thing because lasers allow doctors to have precise control over the size, shape, and depths of the cuts that they make. And in addition, because lasers deposit a lot of energy into the tissue that they're cutting, they seal up blood vessels as they are cut, which minimizes bleeding during the procedure. It's a very beneficial process. So it's used in dental applications for canker sore treatment, among other things. It's also used in vision correction. So this LASIK procedure that helps restore people's vision makes use of lasers to reshape the cornea. So if you look at the diagram of the eye, the cornea is the outermost layer. And in a LASIK procedure, they use one laser to cut a little flap out of the cornea, peel it back, and then use another laser to kind of reshape the eye a little bit to change how it focuses light. And then they flip the corneal flap back over, let it heal for a couple days, and then people see remarkable improvements in their vision correction. So it's like a little miniature lightsaber cutting away at the eye and reshaping it to operate better. Lasers are also used in manufacturing for cutting sheet metal, and the technology is really powerful here. We have exquisite control over the positioning of the laser, and we can make complicated cuts in sheet metal that would be incredibly difficult to reproduce accurately with conventional machining tools. So this is very much like a lightsaber being used to cut apart a piece of sheet metal for high-tech industrial manufacturing. And I also talked earlier about the Death Star, and I want to propose a use of lasers, show you a use of lasers that is kind of like the Death Star, and not in the sense of blowing up planets. We're not interested in blowing up any planets in science. But you see how the Death Star has a bunch of different laser beams, it looks like, that come together to make one central beam. Well, there's a facility just down the road in Livermore, California called the National Ignition Facility, and they have a thing, it looks kind of like a Death Star, that's a vacuum target chamber. This vacuum target chamber is placed in the middle of a big building where they generate 192 laser beams, and they concentrate all of those laser beams into a small target that contains a little bit of like deuterium and tritium fuel. These 192 laser beams hit this target that's held at a temperature of about minus 250 degrees Celsius, and they deliver 500 trillion watts of power over a time period of 20 billionths of a second in an effort to create an X-ray plasma that sustains nuclear fusion, the same kind of fuel process that powers the star at the middle of our solar system. So this is an image, a kind of zoomed-in view at the target that they shoot all of these lasers at. So all those beams kind of converge into one part. And the image on the left is an actual deuterium-tritium explosion that they generated on February 7th of last year. And what they're trying to do with this device is ignite and sustain controlled nuclear fusion as a form of renewable energy. So unlike the Starkiller Base that we're going to see in the current film, which drained all of the energy from a star in order to create a planet-killing weapon, we are taking, or we, the people at National Ignition Facility, are taking lasers to try to create a miniature star in the laboratory to try to help provide us energy to sustain our planet. They also use this not only for energy applications, but to study matter in the environments similar to like the middle of a star. So they use these lasers to help us understand how stars work at a fundamental level. So I hope that you've been able to gain a little bit of an appreciation for the differences between the things in Star Wars and real lasers, but also that lasers are incredibly useful in science and technology. We've seen how we can use them to create star-like environments, study space, learn about the world around us, and even do some better medical procedures. And so I hope you enjoy the film, and I will say that, you know, in science we've discovered many different kinds of forces, right? Electromagnetic, strong, weak, and gravitational. But we've not discovered the force. And so maybe one day we'll discover the force and we too can have the kinds of technology that they had long ago in a galaxy far, far away. Thank you.